Hi guys and welcome to a past paper video. So at the time of the making of this video, the most recent past paper that we do have available right now for us to practice is the March 2024 paper. So this is the most recent paper which is out there. If I had to comment on this paper, so I would say this is slightly tricky, slightly difficult as a paper as compared to the other ones. And again, maybe this is just me, but I've been seeing this trend with these March papers. The March 23 that I did the same time last year, that was also slightly trickier than the usual papers. So nothing to worry about. It's just amazing practice material for you. You can do a final test of your time management skills, and you can also see on what topics you could probably be assessed on. There's going to be a separate video where I'll also be talking about some predicted topics, in my opinion, how they can come in. And those will be supplemented with some questions. But right now, let's get started with this paper. So let's just share the screen here. And let's start. So as opposed to the previous videos that we've been doing, which have been past paper solutions, this one is going to be a past paper walkthrough. What's the difference is that I've solved this paper beforehand. And just to save some time, because obviously so close to your exam, time is really valuable. I have solved it beforehand, and I'll just be going over the reasonings behind those answers. So this allows us to speed through some of those questions that are really straightforward. All right, so we need to go to A2. So that starts from here. All right. Question number 1. Explain why the gravitational potential near to a point mass is negative. Again, if you have been practicing a lot of papers, if you have a good grip on your chapters, you know this is not the first time we have a question like this. Why is gravitational potential negative? Because gravitational force is always attractive. So if something is coming from infinity, the work is done by the force on the mass, right? So the gravitational force does work on the mass. And because we define the potential at infinity to be zero, when something decreases from zero, it's going to be negative. Straightforward. Part B, a planet may be assumed to be a uniform sphere. It has gravitational potential phi at a distance r from the center of the planet. Variation with 1 over r of phi is shown in 1.1. So you have phi on the y-axis, and as we just discussed, this is all negative values throughout, and you have 1 over r here. Phi is in 10 to the 8 joules per kg. 1 over r is in 10 to the negative 8, right? Even before going on to the question, I must be thinking about what this graph really represents. So if I think about the equation, I know that phi is calculated using this equation, negative gm over r, right? So what I have here, this is on my y-axis. This 1 over r is what's on my x-axis. So what remains? Negative gm is going to be the gradient of this graph. It's very useful to think about this even before the examiner pops the question for you. So show that the mass of this planet is 8.8 into 10 to the 25 kgs. So again, phi is minus gm over r, so the gradient is just negative gm. So you can find out the gradient. One nice thing about this graph is that it passes through the origin, so you just need one other point. I've taken this one, which is 4 on the x-axis and minus 2.34 on the y-axis, and I've also written the prefixes with them. 4 is 10 to the negative 8, y is into 10 to the 8. So I just calculate the gradient, which is equal to gm. So it's up to you if you want to first calculate the gradient, then do the math. I prefer this, that I first make the subject and then I just chuck in the values. So gradient and then times minus 1 over the gravitational constant gives us 8.77 into 10 to the 25, which to 2SF is 8.8 into 10 to the 25. Part 2, period of rotation of the planet is 0.72 Earth days. All right, so this is given to us. A satellite, and then I see this word orbit. In all of A2, whenever you see this word orbit, the first thing that should come to mind is circular motion. And you know that if a satellite is in orbit, the force required for the circular motion is provided by the gravitational force. And this remains above the same point on the surface of the planet. So again, this is another place where we have another question on geostationary orbits. If this remains at the same point, this means this is in a geostationary orbit, right? So the conditions for geostationary orbit are three: that you need to have the same direction of rotation as the planet so that it appears at the same position always. Second condition is that it must always also be rotating in the same direction, right? So same period of rotation and same direction. These are the first two conditions. And the third one is that it must be in an equatorial orbit, right? So because we know that this is basically a geostationary orbit, so the period of rotation of the satellite and of the planet are going to be the same, which is 0.72 Earth days. So this thing, Kepler's third law, this derivation, you must have done hundreds of times before doing this paper, if you did do sufficient topical practice. So FC equals FG, I use MR omega square. You've also seen times where I've used MV square over R. It doesn't make a difference. You still get the same final answer. So R cube is GM over 4 pi square T square. And then you just plug in the values. So G, M, which we just calculated. T is 0.72 Earth days because I want my answer in the SI units of meters. My time must also be in SI units of seconds. So each day has 24 hours. Each of those hours is 3600 seconds. And this is 0.72 Earth days. So I multiply with that as well. R cube turns out to be this. So you just take the cube root and R turns out to be 8.31 into 10 to the 7 meters, right? So this is how you do this one. All right, part 3. Speed of the satellite in B2 is 8400 meters per second. Mass of the satellite is 1200 kg. Determine the additional energy required to move the satellite from its orbit to infinity. So the orbit right now is here, right? So this is the planet. This is where the orbit is. It already has some speed. So we know that it also has some kinetic energy corresponding to it, which I've calculated. This is its current kinetic energy. If I want to take this to infinity, you guys know I'm going away from the mass, so GPE is going to increase, right? If I talk about the change in gravitational potential, that would be the gravitational potential at infinity minus the gravitational potential here, right? It's just final minus initial. So 0 minus GM over R is just GM over R. And for the potential energy, I calculate GMM over R. This is the energy that I must provide. So I just plug in the values. Capital M is the mass of the planet, small m is the mass of the satellite, and everything. So I get this as the energy which is required to move it to infinity. But it already has this much energy. So the additional energy is just the difference of the two, which turns out to be the difference. So 8.47 minus 4.23 turns out to be 4.2 into 10 to the 10 joules. All right. This question is something that I don't recall seeing in any of the recent papers, at least. So this was a slightly new question, but in my opinion, not really difficult. And again, you guys know that I like to do this award ceremony for the questions where I talk about the hardest question on this paper. This, I would say, is one of the harder ones, but in my opinion, it's not the hardest one. It's going to come up later. By referring to both kinetic energy and potential energy, explain what is meant by internal energy of an ideal gas. So, internal energy generally is the sum of all the microscopic kinetic and potential energies because of the random motion of those particles. This is also something which is frequently asked. But if you're talking about an ideal gas, there are no forces of attraction, so it also has no potential energy. So the sum of potential and kinetic energies is then just equal to kinetic energy. This is something you should have known while doing ideal gases in theory anyway. Part B, fixed mass of an ideal gas is at the temperature of this much. Again, ideal gas, but the temperature is in degrees Celsius. You must convert this to Kelvin. Initial volume is given. Thermal energy is supplied to the gas, and the volume increases by this much. So thermal energy is given, right? So the gas takes in the thermal energy and the volume increases by this much. Again, this is not increases to, this is increases by. It's a simple play on the English by the examiner. So this is the change. The piston is freely moving, so the gas is always at atmospheric pressure. Atmospheric pressure is given, calculate the work done by the gas. So I have the pressure here. I have the change in volume, which is given. So it's by, so this is the change already. I just multiply the two and correct to 2SF. I get the answer as 5.3 joules. Next part. Calculate the final thermodynamic temperature T of the gas. So because this is an ideal gas, you know, PV over T is a constant. And one way to write this is P1 V1 over T1 equals P2 V2 over T2. But because this moves such that the gas is always at atmospheric pressure, the pressure doesn't really play a role. So what plays a role is just the volume and just the temperature. So I know the initial volume, I was given 20 degrees Celsius. I add 273 to convert this to Kelvin. And the new volume would be the old volume plus the change that we just used in the part above. So this gives us the new volume. From this, we just make T the subject of this equation. Turns out to be 416 Kelvin. The mass of the gas is 16 grams. For this expansion, there is a net transfer of 960 joules of thermal energy to the gas. Right? So 960 is transferred to the gas. Calculate the specific heat capacity of the gas at this pressure. So E equals mc delta T. So energy is given, mass is given, but this mass is in grams. The answer is needed in kg, so I convert this grams to kg. C is what I want to find. And the temperature difference, you guys should also know it doesn't make a difference. If my temperature difference is in per Kelvin or in degrees Celsius, it's going to be the same anyway. So exactly turns out to be 487.8, 3SF, this is 488 joules per kg per Kelvin, right? So this is part 3. Now the last part of this question is, in my opinion, this is a contender for one of the harder questions. But again, in my opinion, this did not win that award still. So this is harder, but not the hardest, in my opinion. You guys may disagree with this. The gas in B is now allowed to return to its starting temperature, right? So because this is an ideal gas, if it again returns to the same temperature at which it started out from, this means there is no change in internal energy. The piston is now fixed in position. So previously it could move freely, now it cannot. So the volume cannot change anymore. So delta V is 0. Thermal energy is still supplied to increase the temperature to the same final temperature as in B. Now, here you need to think about this case that because you're working with internal energy, if you want to increase the temperature to that same value, to that same final temperature, you are basically going for the same change in internal energy. Because of this idea that for an ideal gas, the internal energy is just dependent on the temperature, right? So I want the same increase in internal energy. Use the first law of thermodynamics to suggest and explain how the specific heat capacity of the gas for this situation compares with the value in B3. So if I look at this case here, let's read the question again, the numerical part from the top. So initially the volume was increasing by this much. If the volume is increasing, this means the piston moves out. For the piston to move out, work must have been done by the gas, right? If I think about this according to the equation, the first law of thermodynamics, so I was basically giving in some thermal energy, which is written here. So this thing is positive. But because the work is done by the gas, this thing is negative, right? And this difference of these is what was causing the increase in internal energy. Now here we were given that this was 960 and this was 5.3, right? So whatever 960 minus 5.3 turns out to be, let's just approximate this to just make the values easier to work with. So 960 minus 5, this was 955 joules. So that was the increase in internal energy. Now again, we want the internal energy to go up by 955. That's still what we want. But this time the piston is fixed. So because there is no delta V here, work done is zero. So this means that this thing here, the work done term is zero, right? So in this case, everything which is here, all the thermal energy I provide directly translates to a increase in internal energy. So if you compare these two, previously the thermal energy that I had to provide also had to overcome this term because of the work done by the gas. Now it does not have to do that, right? So now I would not have to supply 960, rather now I would just have to supply the 955 joules of energy. That's all I would need here. So you can see that the thermal energy supplied has gone down, right? This is what I talk about here. So since there is no work done by the gas, less thermal energy needs to be provided for the same increase in internal energy. So less energy needs to be provided. This means that your specific heat capacity is also lower here. This is not the first time a question like this has come up. Winter 22, paper 42, question number 2 is a really similar question. If you are an all subscriber, you can look that up on the platform. We did do a very similar question to this one there, right? So this is also something that I've done so that you guys can practice these similar questions. Question 3, a small object of mass 24 grams rests on a platform. The platform is attached to an oscillator as shown in 3.1. Oscillator moves the platform up and down. Total energy of oscillations is given. In one oscillation, the object travels a total distance of 14 millimeters. So let's say if this what is shown to us is the equilibrium position. So one oscillation is it going up, coming back down, going all the way down, and coming back up, right? This is one oscillation. So if you look at it here, it covers one amplitude, two amplitude, three amplitudes, and four amplitudes. So this distance of 14 millimeters is four amplitudes, which is covered in one oscillation, right? So using this, I divide by 4 to get the amplitude, and then I just use the total energy formula. This is something you are supposed to know. Half m omega square x naught square. M was given 24 grams. I convert this to kg. This is also in millimeters, so I convert this to meters, and I just find out omega square. Right, so omega turns out to be 38.6. So omega is 39 radians per second. Next part, now this one is something which is rather technical. And again, you did not have a question like this for oscillations for quite some time. The frequency of the oscillator is now fixed. So it's moving at the same frequency. The amplitude of oscillations is gradually increased. So if I'm picking something up and if I'm moving it up and down, I'm still moving it up and down at the same frequency, but I'm just taking it more upwards and more downwards, right? So frequency is the same, but amplitude increases now. Calculate the maximum amplitude of oscillation so that the object does not lose contact with the platform. Forget this part for now. Let's just look at some of this practical demonstration here. So this is the equilibrium position, right? When it's at the equilibrium position, we know that there is no resultant force on it, right? At the equilibrium position, because the displacement is zero, because of the defining equation, the resultant force also becomes zero because of this idea that A is proportional to negative x. So displacement is zero, so amplitude is also zero here. So if acceleration is zero. So if acceleration is zero, this means resultant force is zero. So the upwards and downward forces must equal each other out. But then when it goes up, the idea is that the reaction force would reduce. Why do I have this kettlebell here is because if you have ever been to a gym and let's say you're doing this exercise where you have the kettlebell in your hand and you're pushing this up all the way up, when do you feel it sinking into your hand the most versus when do you feel it exerting the least force on your hand? The idea basically is dependent on the principles of inertia. When I do take this below, when I lower my hand with the kettlebell, I feel that it sinks into my hand more and more, right? This is basically because of inertia. Because when it's at the bottommost position and I'm trying to lift it up, the inertia wants to keep it at the same position, right? So that's why I feel it sinking into my hand the most. Versus if it is at the topmost position, so now it has an upward velocity, but right at this position here, right at this position, I am now starting to lower my hand. So it also has some inertia here, which basically causes it to experience a reduced contact force, right? So right at the top, I would find that the kettlebell is not pushing as much into my hand, right? So this is the idea here. Now, if I'm talking about the forces here, at this point where I say that this momentarily loses contact. So this box goes slightly here. So this slightly just loses contact at this point. So I know there is no resultant force. I also know the idea of the resultant force in simple harmonic motion is that it is also known as the restoring force because that force always acts towards the equilibrium position. So in this case, if I think about the resultant force, that is obviously downwards, and that is just equal to W, right? Even though this is not asked in this part, I'm still going to talk about this just for clarity. If I talk about resultant force in this position where we are lifting this right from the depths to that equilibrium position right now, in this case, the resultant force would be upwards, right? Because the restoring force is always towards the equilibrium position here. So in this case, the resultant force would really be R minus W. This is not asked, but I'm just talking about this for general knowledge. So when the contact is lost, the idea is that the resultant force is just equal to the weight because the reaction force goes away. This is exactly what I've used in the calculations here, right? So actually it would be W minus R, but R goes away, right? Why is it minus R? Because the reaction force, usually, if I'm talking about any position at the top, so this is going to be upwards. So this basically goes away now when it loses contact. So if I write out the equation for force, so force here is mass times acceleration, just the resultant force should equal the weight, which is mass times acceleration due to gravity. You see that masses cancel out and the acceleration of this object is equal to the acceleration due to gravity when it loses contact. Another really important thing to think about. And the idea is this. If I have this object in my hand right now, you know that if I drop this really fast, there could be such a position where it does stay in the air, but my hand moves downwards. But if I'm just normally moving this, this is not losing contact. But if this acceleration is very fast, it will lose contact. The limiting condition is really this, that if the acceleration downwards, if this is greater than the acceleration due to gravity, it will lose contact. Because the hand is moving faster, and for a while, that object will stay in air before falling downwards, right? So if it accelerates faster, if the platform basically accelerates faster, there will be a time where the object will be in air. This is where the contact is lost. Acceleration I know is omega square x naught equals g omega square omega I found out. So x naught, the max amplitude I just find using this equation, right? So this amplitude I have then found out. Again, a similar question to this one was summer 18, paper 41, question 2. You guys might want to check that out as well because it's very similar to this one. Amplitude of oscillations is increased so that it is greater than the value in B1. So greater than the value in B1 means that the amplitude is now greater than this, right? What was this? This was the amplitude. This was the extreme amplitude it could go to without losing contact. Now it's increased more than this value, right? Now, State and explain the position in an oscillation where the object first loses contact with the platform, right? Now, obviously, because of all of this analysis we've doing, you also know this by experience, the position where contact would be lost first would be at the topmost position of oscillation, right? The reason is that for contact to be lost, the reaction force is zero, right? So this happens when the force is the greatest. So the acceleration towards the equilibrium position, basically downwards, is greatest. And it is greater than the acceleration due to gravity, right? So that the platform goes down faster, then the object can fall because of its own weight. If you guys did this math with a little bit of thinking as to what this means, this just comes to you naturally, right? So one mark you get just for stating what this position is, and the other mark is for explanation. So this was a really conceptual question. Three capacitors are connected as shown in 4.1. You have two in parallel. So how we deal with capacitors in parallel is how we deal with resistors in series. We just add them up. And then this combination is in series. So then I use product over sum. So 10 plus 20, which is 30, times 45 over 30 plus 45, that turns out to be 18. Part B, a capacitor of capacitance 45 microfarads is connected to a variable power supply set at 8 volts. Output of the power supply increases so that the potential difference increases to 9.6 volts. Calculate the energy, the increase in energy stored in the capacitor. So you know that the formula is half CV square. So the increase would be half C delta V squared. So again, as we used to do in AS with the kinetic energy formulas, we subtract the squares and we don't. So it's the difference of the squares, not the square of the difference, right? So it's 9.6 square minus 8 square, not 9.6 minus 8 square, right? That's just how the formula works. If you find this is a bit difficult to remember, you can just write out the final energy using this voltage, initial energy using this voltage. So this would be half times this times 9.6 square minus half times this times 8 squared. Again, you would get the same answer. C1, a sinusoidal AC supply is connected to the input of a bridge rectifier. Output of the rectifier is connected to a load resistor. Complete the circuit in 4.2 by adding a capacitor to smooth the potential difference. So we know that we have a capacitor in parallel for that purpose. Variation with time t of the PDV of the smoothed output is shown in 4.3. Determine the time constant in milliseconds of the smoothing circuit. So we have the voltage and how it's decreasing. So I know that voltage follows an exponential decay in this case across the capacitor. That's how the voltage across the capacitor decreases. So I know this is the equation. V equals V naught e to the negative t over RC. Because I want the time constant tau, I substitute that into my equation. Then it's up to you as to what voltages you select. I selected the max voltage 4, and it goes to this value 3.2 in a time of 8 milliseconds, right? 4 to 3.2 in a time of 8 milliseconds. So from 5 to 13. It's up to you whatever voltages, whatever voltage values you want to use. If you wanted to, you could have also used something in the middle. I just use the ones which are very clearly observable, right? So that I don't lose any silly marks here. So 3.2 is the final voltage after that 8 milliseconds. 4 was the initial voltage, e to the negative 8. I did not convert this here because the time constant is also asked in milliseconds. And then I just take the ln. So I do 3.2 over 4. To get this down from the exponent, I take ln. So ln e basically becomes 1. This comes down as the power. So that is minus 8 over tau. Then you just plug this in into your calculator and make tau the subject. Part D, a sinusoidal AC power supply has a max power of 16 watts. State the value of the mean power when the output of the power supply is full wave rectified. So the idea is this, that when we talk about RMS powers as of a full wave rectified sinusoidal wave, So the idea is that the power becomes half. Why is this so? Because the derivation is really simple. I've also covered this in my AC lectures. So PRMS, you can say is VRMS, IRMS. If I write this as my peaks, so I would write this as my V peak over root 2. Similarly, RMS I would write as IP over root 2. So there's a root 2 square in the denominator, so that's VPIP over 2. And what is VPIP? This is just your peak power, which leads to this expression here. So the power gets halved. For a full wave rectified output, this is how the mean power is. How about the half wave rectified? So the idea is that if I did make a full wave rectified circuit here, a full wave rectified waveform, let's try to make this. So this is what it would look like, right? I have all of this now recovered. So this is what it looks like for the full wave rectified circuit. But for the half wave, what happens is now even half of this is lost. So now this goes away, this goes away. And in the middle, I have no voltage at all. So the power gets halved further, right? Because of the elimination of half of the wave, the power gets halved further. So from 8 divided by 2, that becomes 4. Question number 5. An object travels in a circle at a constant speed. State the names of two quantities that vary during the motion of the object. So velocity obviously varies, and related to velocity, you can also write momentum. Acceleration also varies because of the change in direction. The magnitude is the same, but because the direction is always changing, that also changes. Or derived from that, you can also write the resultant force. Part B, this derivation was slightly tricky, especially if you don't like math. A charged particle of mass m and charge q enters a region of uniform magnetic field perpendicular to the field lines. The magnetic flux density is B. The particle travels in a circle with period t, radius r. By considering the magnetic force, you have to prove this expression. Now, the initial thing is, I guess, pretty easy to identify that here the centripetal force is provided by the magnetic force. Because this is a charged particle, we use BQV. Now, when I use this equation, the first thing I see is that there is no omega. So this makes sense that I see 2 pi over t. So in some way, the examiner must have substituted instead of omega 2 pi over t. But another problem is this, that I don't see v either. Now, if you remember some expressions, so one of these expressions, because I remember them, is this one, that R equals mv over bq, right? You can also see this forming very easily here. But in this case, you don't have any v here. So for the v, I also substitute 2 pi r over t. This is what was different, what you had to identify as the need of this question, and then you had to do this. So when you expand the brackets, this becomes mr 4 pi square over t square, and bq 2 pi r over t. Then some cancellation happens, r's cancel out, some of the t's cancel out, some of the pi's cancel out, 2 and 4 cancel out partially. So you have 2 pi m over t equals bq. Now it's really easy to see that b is 2 pi m over qt, right? Part 2. The particle is an alpha particle. The period of the circular motion is 2.5 microseconds. Calculate B. So you just have to use the expression alpha particle. So you know the mass is 4u. U is this value. Q is 2e. So 2 times 1.6 into 10 to the negative 19. Just plug this all in here, right? So this turns out to be 0.05215 or to 2SF 0.052 Tesla. A second alpha particle is in the same uniform field. It travels in a circle of radius 2r. State and explain how the periods of the motion of the two particles compare. From this expression, if you were to make t the subject of this equation, you would see that it's 2 pi m over bq, right? So it depends on m, b, and q. It does not depend on the radius r. So the answer is that there is no change since the r's basically cancelled out here in this step of this working, right? So the time period does not depend on r. You can say that the time period just depends on b, m, and q, right? All right, next part. Speed of the alpha particle is now this much, an electric field is applied so that the particle now moves with constant velocity. Use your answer in B2 to calculate the electric field strength. Give the unit with your answer. So for this to now move with constant velocity, this means that both of these forces cancel each other out. So magnetic force equals to the electric force. BQV equals QE. Q's cancel out. And if you haven't recognized this still yet, this is a question on velocity selectors, right? So E equals to BV, you know B from a previous part, V is given, you just multiply them. Unit could be Newton per Coulomb, could be volts per meter, whatever you like. This is the answer you get. Question number 6. Small coil has 64 turns, cross-sectional area is in centimeters square, so I would need to convert this. Coil is placed inside a solenoid as is shown in 6.1. Center of the coil C is on the central axis of the solenoid. So it's moving along this line, all along this line. It's not moving vertically up or down. There is a constant current in the solenoid. Coil C is moved through the position from position X to position Y. On 6.2, sketch a line to show the variation of the magnetic flux linkage in coil C with position as it moves from X to Y. So magnetic flux linkage is N phi, which is NBA. Number of turns is not changing here. Magnetic flux density, which it experiences, that is also not going to change because inside this coil, if I make the field lines, they would be like this. They would be equally spaced, right? So the magnetic field strength, or what you call an A2 magnetic flux density, that's the same. And obviously A is also not changing. So you have a constant value for the flux linkage. The reasoning for this is asked in the next part. So magnetic flux linkage is NBA. N and A are constants. And since because we were given this, that the current is constant, so B is also the same. Coil C is now held stationary at X, and now the current is varied, that the magnetic flux density at X varies from time 0 to 40 as shown. Calculate the max magnetic flux linkage. So again, N phi equals NBA. You have N, you have A, you just need the max B, which is this one, and you find out the answer. It turns out to be this. Again, our area was in cm square, so I did have to convert to meters square. So because 1 meter is 10 to the 1 centimeter is 10 to the negative 2 meters, so squaring that gives us 10 to the negative 4. On 6.4, sketch a line to show the induced EMF in coil C from time t equals to 0 to 40. So in doing so, we use this idea that the induced EMF is the rate of change of magnetic flux linkage, right? So we're really taking the gradient of the magnetic flux density graph. Here there is no change, so there would be no induced EMF. Here the EMF increases, right? It's increasing at a constant rate. So my value is going to be a constant. So this is the positive constant from t to 2t, because that's the part during which this was rising. And then it's reducing from 2t to 4t. And if you look at the gradients, both of these gradients are equal. So they will give rise to equal magnitudes of EMF. But because this was an increase and this is a decrease, both of these EMFs will have different polarities. So I draw the same magnitude. So it's two boxes. This is also two boxes, but it's in the opposite direction. Another possible answer could also have been that if you accommodated Lenz's law here and you do take into account the negative sign, then this also could have been a possible answer, right? So this would also be true. So it could be either this or that. All right. Again, this is a question where you do have a similar question. Again, if you're an all subscriber, you have this on the platform as well. Summer 21, paper 42, question 9. Metal spring rests on a smooth table. Turns of the spring are equally spaced. Ends of the springs are connected to a DC supply. Spring is connected to the DC power supply using flexible leads. Spring is not under tension. With reference to magnetic fields, describe and explain the change in distance between the turns of the spring when the power supply is first switched on. So when the power supply is switched on, you basically have a solenoid of sorts here. You have turns of wire. These are turns in the spring, which are going to carry current. And the idea is that the first thing to identify is that they would all be carrying current in the same direction. This is the most important thing to see. So current goes here, then out of here. So all of the adjacent turns, they take current in the same direction. It says with reference to magnetic fields, explain the change in the distance. So first off, I know that there is going to be current in the spring, which creates a magnetic field, right? So there is going to be current in the spring, which is going to create a magnetic field of its own. And then we have the neighboring turns, which are also going to experience a force, which is mutually perpendicular to the field and current, right? So if I'm talking about the left-hand rule, all of these variables, the force, the field, and the current, all are mutually perpendicular to each other, right? So this is what it means. Again, probably I should reword this because it does say with reference to magnetic fields. So I should probably reword this and maybe write it like this. So maybe I should write it like this. Because of the interaction of the magnetic fields. Because of the interaction of the magnetic fields of the turns. Right? So you have all of those magnetic fields, and when their magnetic fields will interact, this is going to create some force. Now, how will you explain what happens to the distance between the turns? So that is identifying that since all of these take currents in the same direction, these are like currents, so they will attract, right? So the turns come closer together, the distance reduces. We have had a really, really similar question in this paper. So be sure to check this out if you got stuck in this one. All right. Question 7. A photon has energy this much. Calculate the momentum of the photon. So P equals to E over C, right? This is the equation that you use here. So this is given. The energy is given. So you use E over C. E is this, C is speed of light, and you get this as the momentum. A laser beam has a power of 350 milliwatts. Light from the laser has this wavelength. Determine the number of photons emitted by the laser in a time of 1 second. So if you're talking about 1 second, so this energy really becomes this power really becomes the energy. So I can say that in 1 second, I get 350 millijoules of energy. In doing so, I use this idea that the energy of this radiation, which is 350 millijoules, is the number of photons times the energy of each such photon, right? So 350 milliwatts is my total energy, and energy of a photon I can calculate using HF. Because I have wavelength provided, I use hc over lambda, right? So N is E over E photon. This is E, and the energy of each photon is given by this equation. So hc over lambda. So that turns out to be this value here. Part 2, the laser beam is incident normally on a surface that absorbs all of the photons. So the photons cease to exist after they strike the surface. Show that the force F exerted on the surface is given by this equation where P is the power, C is the speed of light. So I see force, as should be the case, the first thing that comes to mind is force is the rate of change of momentum. Now, because there is no final momentum, because all of these are absorbed, the change in momentum, the magnitude of that is just the initial momentum. So I have the initial momentum divided by time. And what I just used above is that P can be written as E over C, right? P can be written as E over C. So instead of P, I write E over C, and there's also a T. E over T becomes power over the speed of light. Light of a single wavelength is incident on the surface of different metals. Work function energy of the metals is given. These are all in electron volt. Explain the term threshold wavelength. If you know the threshold frequency, you just have to play around with this a bit to get the threshold wavelength. Because you know frequency is inversely proportional to wavelength, the threshold frequency was the minimum frequency in which emission occurs, right? So before this frequency, no emission occurs. Similarly, the wavelength, the threshold wavelength is the max wavelength. After this, if you increase wavelengths further, then no emission occurs, right? Part two, for tables, for the metals in this table, calculate the value of the largest threshold wavelength. Again, I use the same idea. Largest wavelength means the smallest frequency, means the smallest energy, right? So since pi was hf naught, if I want to calculate the wavelength, I write this as hc over lambda naught. So I need the smallest energy, so I use potassium, right? So that's 2.26 because this was electron volts. I convert to joules by multiplying by the fundamental charge, and then I just use this equation, and lambda naught turns out to be 550 nanometers or 5.5 into 10 to the negative 7 meters. Question number 8. What's meant by the binding energy? So energy required to split all of the nucleons in a nucleus to infinity. 1 mark is for saying for any indication of you splitting the nucleus into its nucleons, and the other mark is for saying to infinity. Nucleus of uranium-235 absorbs a neutron, becomes unstable, undergoes a fission reaction. One possible reaction is given. Determine the number of neutrons produced. So here you use the conservation of nucleon number. So 235 plus 1 equals 142 plus 90. And because neutrons have a nucleon number 1, so I've written n times 1, where n is the number of neutrons. Just rearrange and find out n, which turns out to be 4. Data for binding energies per nucleon for this fission reaction are given in mega electron volts, right? And the answer is also required in mega electron volts, so that's good to know. Calculate the energy released. So you just take the differences in the total binding energies of the products and the reactants. This was the reactant, right? Obviously, this would not have any binding energy because this is not a nucleus right now. It's just a nucleon, it's a particle. So this is my reactant, this is my products. I just take the difference, which turns out to be this value. So because this is binding energy per nucleon, I multiply by the number of nucleons to get the total binding energy. Because this was uranium-235, it has 235 nucleons. 235 times this, 142 times this, 90 times this is what you have. Reactant, products, add the products, subtract the reactants. Whatever you want to do, again, you just want to look at the magnitude of energy, right? So the negative sign don't really mean a lot to us. So 189.69, which turns out to be 190 mega electron volts as the answer. Isotope xenon 142 is unstable. The isotope xenon 132 is stable. Suggest why xenon 142 is unstable. As you can obviously see, it has a greater nucleon number, which is probably why it's unstable. So it has too many neutrons, which make the nucleus too heavy. Part 4, xenon 142 decays into cesium 142. A sample initially contains only nuclei of xenon 142. After a time equal to 6 seconds, the ratio of the number of decayed nuclei to the number of undecayed nuclei is 31. Calculate the half-life of xenon 142, show your working. I see the word half-life. This equation is the first thing that should come to mind. The exponential decay of the exponential equation associated with radioactive decay. So n equals n naught e to the negative lambda t. This is what I should use. If I just try to make sense of this ratio, so the number of decayed nuclei would be the number of initial nuclei minus the number of nuclei which remain. In this equation, when I give any value of time, and if I give any value of initial nuclei, I get the number of nuclei remaining at that particular time. But we don't want the nuclei remaining. We want the ones that have decayed. So that's the initial minus what remains. So n naught minus n over n. If you just do some math here, so if you like separate the denominator, so n naught over n minus n over n, which is 1. So n naught over n is 32. Now that you have a relationship between n naught and n, you can use it together with this equation. So n naught over n would be 1 over e to the negative lambda t, which is going to be 32. It's just math from here on out. You do make this 1 over 32, you take the ln. So this becomes ln 1 over 32. And after taking the ln of e, you just have the power left minus lambda. T was 6 seconds. 6 seconds right here, and you find out lambda. And then for t half, you use lambda t half equals to ln 2, and you get the half-life as this. Again, this is also a contender for hardest question because of the math. Also, I hardly ever say this, but I feel like this one should have been maybe worth like 4 marks, maybe, because of the sheer amount of algebra involved with this part. But again, it is what it is. 9. Electrons in a vacuum are accelerated through a potential difference of this much. Electrons strike a metal target. X-rays are produced. Calculate the minimum wavelength of the X-rays which are produced. The minimum wavelength corresponds to this idea that all of the electric potential energy which the electrons have, all of that is transmitted to the photon energy, right? So HF is what I would say. Because I need wavelength here, I use HC over lambda. So lambda naught, the minimum wavelength, it turns out to be this value just by using this equation, right? HC, Planck constant, speed of light. V, the accelerating potential difference is given, and Q is the charge of an electron. Melting point of two metals are given. You have copper and tungsten. Suggest why the metal target is made from tungsten rather than copper. Again, it corresponds to the idea that we were just talking about moments ago. Why is this the minimum wavelength? Is because some of the energy is also gone in basically making that target metal hotter, right? Now, because this has a higher melting point, so this is less likely to melt, right? So that's the answer to this one. An X-ray beam is incident normally on a sample of soft tissue and bone as shown in 9.1. Data for the two materials are given in 9.2. So you have the mu values as well as the z values given for both of these media. Total thickness of soft tissue is X. Total thickness of bone is also X. So this and this also combine to give you X. And this alone is also X. This is what the question means. All right. Intensity, incident intensity of the beam is I naught. Transmitted intensity is 13% of the incident intensity. Determine X in centimeters. So in this one, if you talk about the incident intensity, so this is the intensity which just comes into the medium, right? This is the intensity which comes in. This is I naught. They say that the transmitted intensity, so the one right at the end, is, as opposed to this one right at the end, this is 13%, right? So if I call this I, so I use the exponential decay equation for attenuation as well, which is that I equals I naught e to the negative mu x, right? Because this is 13%, I can say that my I is 0.13 times I naught, right? Because I'm using soft tissue as well as bone, the idea is that uh, these effects are compounded basically. right? Because the intensity which comes out of one of those then goes as the incident intensity on the other medium. Also, the orders do not make a difference. So, for example, if I had, what do you call it? If you had bone first and then soft tissue and then bone and then soft tissue, that would also not make a difference as long as the total lengths are the same. We've also covered this in a recent past paper video. So you just multiply both of these E values together. So both of these have the same thickness as X. So you have negative 0.22 and negative 3x because of an indices rule. When bases are same and these variables are multiplied, powers are added. So this becomes negative 3.22x. Again, you take the ln and x turns out to be 0.63 centimeters, right? So we're seeing a lot of math in this paper up till now. Define specific acoustic impedance. So I'm really using this equation, Z equals to rho C. So density times speed of the ultrasound in that medium, that specific acoustic impedance. Use data from 9.2 to calculate the percentage of intensity of ultrasound that is transmitted at a boundary between soft tissue and bone. So you know that using the Z values, I calculate the intensity reflection coefficient alpha, which is the ratio of the reflected to the incident intensity, right? So Z2 minus Z1 square over Z2 plus Z1 square. Again, I don't even have to bother with the 10 to the 6s. They will cancel out anyway. So their difference squared in the numerator, their sums squared in the denominator, right? All right, I don't know if I repeated myself. So difference squared in the numerator, sum squared in the denominator turns out to be 41.2%. So if 41.2% is reflected, this means the remaining, which is 59%, 58.6, so 59% is what is transmitted. Next part is really important. Again, another contender for hardest question. Ultrasound is now incident on the sample of soft tissue and bone as shown. Suggests two reasons why the transmitted intensity is less than the answer in C2. So what's the idea here? What we just did in this case and in actually in both of these numericals that we did, you know, the one thing that we did is that we did not take any care of this idea that what boundary is before, what boundary is after, right? Also, we did not take into account the ideas that you have a lot of different boundaries here. I mean, it is a soft tissue and bone boundary always, but there are multiple boundaries here. It's not like you just have some soft tissue and then you have some bone. There are like you have soft tissue bone, then after bone you have soft tissue again, then after soft tissue you have bone again. So you have soft tissue, then bone, then soft tissue, right? So the idea is that if I'm talking about this practically, when this X-ray beam enters, there is going to be some transmission and reflection at this medium. Similarly, when it reaches here, there's going to be some transmission and reflection at this medium as well. This is one thing that we have not taken into account in our calculations. The other thing is this, that we also did not talk about the attenuation which happens when talking about the transmitted intensity, which was the answer in C2, right? The idea is that we said that at a boundary between soft tissue and bone, we just treated the I naught, the incident intensity, as what would be striking each boundary as well. But this is wrong. Because if this is I naught, in going till here, it would also be attenuated through that small distance. So this is why the value is actually less than what we calculated. So the ultrasound is also attenuated before reaching the boundary, and you have partial reflection and transmission at each of the boundary, which also reduces the intensity. Question 10. Sun has a surface temperature of this much. Luminosity is given. Calculate radius. So you have T, you have L, you are asked radius. So we use the Stefan-Boltzmann law. So L equals to 4 pi sigma r square T4. So you just plug all the values in. This is r squared, remember. So you would need to take the square root. which turns out to be 6.96 into 10 to the 8 meters. Earth is at a distance of this much from the sun. Calculate the radiant flux intensity of the radiation. So I had L above. I now know the distance. So I just use the radiant flux intensity formula and I get the answer. Again, because this is intensity, it's going to have units of power over area. So watts per meter square. And this is what the value turns out to be. All right, part 2. Variation with wavelength of the intensity of radiation emitted from the sun is shown in 10.1. So this is an intensity wavelength graph that we have here. And also just looking at this, you must be able to also identify a point that this is really your lambda max, the wavelength corresponding to the max intensity of radiation, right? So this is what lambda max is. It says it has the same radius but a lower surface temperature. Sketch a line to show the variation with wavelength of the radiation emitted for this star. So because its temperature is lower, Stephen Boltzmann law tells us that the luminosity would also be less, right? Temperature is less, so luminosity would also be less. There's this direct proportion that we're using here. So if one thing goes down, the other thing also goes down. Next, because the temperature is low, and because I know of Wien's law, which is this idea that lambda max T is a constant, I also know that because of my temperature being lower, the wavelength corresponding to the max intensity of radiation, this would go up. So my wavelength is now going to be further out towards the right, and it's now not going to have that much of the max intensity because luminosity has gone down. So my graph in this case would look something like this. And this is what my new lambda max would be. You don't have to label it, but I'm just talking about this, how what this peak represents. Again, slightly tricky. A galaxy in the constellation of Corona Borealis, again, this word just gives me trauma, is moving away from the Earth. So visible emission spectrum of sun is shown. So you have some wavelengths. Lines are at wavelengths 397, 410, 434, 486, and 656. Compositions of the sun and a star in this galaxy are similar. On 10.3, sketch the emission spectrum for the star in this galaxy as is observed from the Earth. No calculations are required. As with most of these galaxies, because this galaxy is moving away from us, we know this radiation is going to be red shifted. What does redshift mean? It means an increase in the observed wavelength. Or you can say a decrease in the observed frequency. Means the same thing. So I have the same wavelengths, but slightly shifted out towards the right. So what I literally just did, I took a screenshot of this and I pasted this, but slightly further out to the right. So this becomes this value, this becomes this value, this becomes this value, this becomes this, and this value becomes this one. So all of the wavelengths are red shifted, right? So the wavelengths have increased. The galaxy in Corona, again, sorry, the galaxy is moving away from the Earth at a speed of this much. Use information from B1 to calculate in nanometers the observed wavelength of the lowest visible energy emission. Lowest visible energy emission means that if you want the energy to be the lowest, frequency must be the lowest, and hence the wavelength must be the largest one. Because you need the observed wavelength, so you use this formula because you are given the speed. So delta lambda over lambda equals V over C. So lambda, again, I use the max lambda, which was 656 nanometers here. And I just plug this into the equation. Delta lambda turns out to be 46.79 because you know this is redshift. Observed wavelength would be larger. So to this wavelength that I had, I add this basically this amount of redshift and I get the value for the new wavelength. Turns out to be 703 nanometers to 3SF. Last part, also tricky. Wavelength in B2 is used to calculate a value for the surface temperature of the star in the galaxy. The calculation does not give an accurate value. State and explain whether this value of temperature is too high or too low. So what we use here is that we use the maximum. So we use the wavelength that we calculated corresponding to the max wavelength, and we used that to find the surface temperature. So we must have used Wien's law. Lambda is inversely proportional to T. Now, because we did use the max wavelength without even saying whether this is the max intensity or not, probably the lambda value we used was overstated. It's more than it actually is, right? So because my lambda here is overstated because of this inverse proportion, the temperature is understated. Because lambda, the wavelength, was more than it actually is, the temperature is less than it actually is, right? So this is the reasoning for this part. And this is the end of this paper. So definitely not an easy paper, many tricky parts. But yeah, if you guys did manage to do well on this, so congratulations to you. And know that you are very well prepared for your exam. Those who did not manage to do so well, do watch this video all the way from start to end and try to find out what went wrong for you. All right. Don't stress this out, guys. You guys have prepped a lot. Just be confident in your abilities and just make sure that you do your best. Right. The only competition you have is with yourself. So thanks for your time, guys. Best of luck for your exams. All of us are rooting for you. May you get all and more than what you deserve. So thanks for your time and then see you later. Bye.